Detroit, Michigan, November 1932. The factory floor of Brown and Sharp Manufacturing lay silent under the pale morning light filtering through industrial windows. 52-year-old James Norton stood before a machine that his entire engineering staff had advised against purchasing, a surface grinder that promised precision his competitors called impossible. The machine looked deceptively simple. A rectangular table moved beneath a spinning, grinding wheel, its motor humming at frequencies that made traditional machinists uncomfortable. Unlike the familiar bite of milling cutters that shaved metal in predictable chips, this grinder whispered across steel surfaces with abrasive wheels that most mechanics viewed with suspicion. Norton had mortgaged his family's savings to purchase 3 of these machines from a struggling Massachusetts manufacturer. His decision came not from confidence, but from desperation. The Depression had devastated American manufacturing, forcing machine shops to compete on quality rather than volume. Traditional milling methods delivered components within thousandths of an inch, adequate for most applications, but insufficient for the emerging precision industries that demanded tolerances measured in millionths. The skepticism surrounding surface grinders ran deeper than simple unfamiliarity. Experienced machinists had spent decades mastering the art of milling, learning to read the sound of cutting tools, feeling the resistance of metal through their hands, judging surface quality by eye and touch. Grinding eliminated these tactile connections, replacing craftsman intuition with what seemed like guesswork about invisible abrasive particles removing microscopic layers of metal. Martin Wheeler, Norton's senior machinist with 30 years of experience, circled the new grinder with barely concealed contempt. "You've bought 3 very expensive paperweights," he announced to the gathered workers. "Grinding is what you do after real machining is finished. To clean up surfaces, nothing more. This machine can't hold tolerances under production loads. The wheel wears unpredictably. The heat generated will warp the workpiece. Any fool knows you can't build precision components by rubbing them with a spinning stone." The technical concerns Wheeler raised reflected industry consensus that had developed through hard-earned experience. Early grinding machines, crude affairs with unbalanced spindles and imprecise tables, had indeed produced inconsistent results. Grinding wheels shattered without warning, sending shrapnel across factory floors. Thermal expansion from grinding friction introduced dimensional variations that negated any theoretical precision advantages. Most damning of all, the process seemed impossibly slow compared to milling operations that removed metal in visible curls rather than invisible dust. Norton absorbed these criticisms while calculating a different mathematics. His primary customer, a manufacturer of precision gauges for the automotive industry, had begun rejecting components that met existing specifications but failed new requirements for surface flatness measured in millionths of an inch. Traditional milling methods, regardless of operator skill or machine quality, left microscopic tool marks that compromised absolute flatness. If grinding could deliver the mirror finishes his customer demanded, the slow speed would become irrelevant compared to the elimination of rejected components. The morning of November 15, 1932, James Norton made a decision that would either save his company or complete its destruction. He ordered his entire production staff to begin training on machines they didn't trust to perform work they didn't believe possible. The case against surface grinding rested on technical foundations that seemed unassailable to experienced machinists. Traditional milling operations removed metal through clearly understood mechanical principles. Rotating cutters with defined geometries engaged workpieces at calculated feed rates and depths of cut. The physics were straightforward, the results predictable, the quality dependent on operator skill and machine rigidity. Grinding introduced variables that defied the craftsman's intuitive understanding of metalworking. Instead of a single cutting edge with known geometry, grinding wheels consisted of thousands of randomly oriented abrasive particles embedded in bonding material. Each particle removed microscopic amounts of metal through a combination of cutting, plowing, and rubbing actions that generated tremendous heat concentrated in tiny contact zones. Robert Jamieson, representing the American Society of Mechanical Engineers, had published a comprehensive analysis in 1931 that quantified the problems with grinding as a primary machining method. His research documented how grinding wheels wore unevenly, changing their effective diameter during operation and introducing dimensional errors that accumulated unpredictably. The abrasive particles dulled at different rates depending on the hardness variations within the workpiece metal, creating surface inconsistencies invisible during grinding but revealed through subsequent measurement. Most concerning to production managers, grinding generated heat that traditional flood coolant systems struggled to control. Temperature variations of just a few degrees Fahrenheit could cause steel components to expand by millionths of an inch, precisely the tolerance range that grinding supposedly controlled. Jameson's calculations suggested that attempting to hold tolerances tighter than 5/10,000ths of an inch through grinding would prove economically impractical due to the thermal management requirements. The cost analysis appeared equally damning. Milling machines, operated by skilled machinists, could remove metal at rates measured in cubic inches per minute. Surface grinders, even under ideal conditions, remove material at rates measured in cubic thousandths per minute, a thousand-fold difference in productivity. The grinding wheels themselves required frequent dressing to maintain sharp cutting edges, adding operational costs that milling operations avoided through simple tool changes. Factory managers reviewing Norton's decision to invest in surface grinding technology calculated return on investment scenarios that suggested bankruptcy within 18 months. A single milling machine, operated by an experienced machinist, could produce more finished components in a day than 3 grinding machines operated around the clock. The precision advantages that Norton believed grinding would deliver seemed theoretical compared to the mathematical certainty of production economics. The human factor amplified technical skepticism. Machinists had invested years developing the skills necessary to achieve precision through traditional methods. Their professional identity derived from the ability to read micrometers, adjust cutting parameters by instinct, and deliver quality through practiced technique. Grinding machines threatened to devalue these hard-won abilities by substituting mechanical precision for craftsman skill. Wheeler organized an informal meeting of Norton's senior machinists to document their collective concerns about the grinding machines. Their list of objections filled 3 pages with detailed technical arguments about why grinding could never replace milling as a primary production method. The conclusion seemed inescapable. James Norton had bet his company's survival on technology that violated every principle of practical manufacturing economics. The only question remaining was how quickly the mistake would become catastrophic. The challenge arrived on a gray December morning in the form of a telegram from Pratt & Whitney, one of America's premier manufacturers of precision measuring instruments. Their specifications demanded flatness, tolerances of 2/millionths of an inch across gauge blocks measuring 4 inches square, requirements that seemed to transcend the capabilities of any production machining method available in 1932. Norton read the telegram twice before calling his engineering staff together. The order represented either salvation or final confirmation of his catastrophic judgment. If his grinding machines could deliver the specified precision, the contract would generate enough revenue to sustain operations through 6 months of depression economics. If grinding failed to achieve the impossible tolerances, Norton would have demonstrated to the entire industry that surface grinding belonged in experimental laboratories rather than production factories. Martin Wheeler examined the Pratt & Whitney specifications with the methodical attention of a surgeon reviewing a terminal diagnosis. 2/millionths across 4 inches, he announced slowly, ensuring every machinist understood the mathematical absurdity. That's equivalent to maintaining perfect flatness over a distance equal to the length of a football field with height variations no greater than the thickness of a human hair. Milling operations achieve 10,000ths under ideal conditions. You're asking for precision 5,000 times better than what traditional methods deliver. The technical barriers seemed insurmountable through conventional analysis. Steel components expanded by approximately 7/millionths of an inch per degree Fahrenheit of temperature change. Maintaining 2/millionth tolerances would require thermal control systems that didn't exist in standard machine shops. The grinding wheels themselves would need to maintain dimensional stability while removing metal at rates slow enough to prevent heat buildup, a contradiction that suggested the entire specification existed outside practical manufacturing reality. Norton made a decision that his machinists interpreted as either inspired or delusional. Rather than declining the contract or negotiating more achievable specifications, he ordered Wheeler to begin grinding trials using the despised machines that still gathered dust in the corner of the shop floor. The senior machinist's objections filled the factory air with technical arguments about why the attempt would fail, but Norton remained unmoved. The first test piece, a simple 4-inch square block of tool steel, went onto the grinding machine on December 18th. Wheeler supervised the setup with the careful attention of someone documenting inevitable failure. The grinding wheel, a carefully selected aluminum oxide composition bonded with vitrified ceramic, began its first pass across the steel surface at a feed rate that seemed glacially slow compared to milling operations. What happened next violated every prediction that Wheeler's experience had generated. Instead of the irregular surface that grinding skeptics expected, the steel block emerged with a finish that caught overhead lighting like polished glass. The surface reflected Wheeler's face with mirror clarity, a visual indication of flatness that no milled surface had ever achieved in his 3 decades of machining experience. The dial indicator measurements told an even more remarkable story. The maximum height variation across the entire 4-inch surface measured less than 5/millionths of an inch. The grinding machine had achieved in its first trial run precision that exceeded milling capabilities by factors that seemed to belong to theoretical discussions rather than production reality. The unexpected success of the initial grinding trials forced James Norton's engineering team to confront a fundamental question. Why did grinding achieve precision that violated every prediction based on conventional machining theory? The answer lay in physics that traditional machinists had never fully understood because their experience with grinding had been limited to secondary finishing operations rather than primary precision work. Thomas Anderson, a young mechanical engineer Norton had hired fresh from MIT, began systematic analysis of the grinding process using measurement equipment that revealed mechanics invisible to craftsman intuition. His findings challenged assumptions that had governed American metalworking for generations. The key insight involved understanding how grinding removed metal compared to traditional cutting operations. Milling cutters, regardless of sharpness or rigidity, deflected microscopically under cutting forces, creating tool marks that represented the cutter's path variations. Even the finest milling operations left surface patterns, microscopic ridges and valleys that followed the helical path of rotating end mills or the linear travel of fly cutters. Grinding eliminated these tool path marks through a fundamentally different material removal mechanism. Instead of a single cutting edge deflecting under load, thousands of abrasive particles each removed fragments of metal measured in millionths of an inch. The cumulative effect averaged out individual particle variations, creating surfaces with roughness measured in micro-inches rather than the 10,000ths typical of milled finishes. Anderson's measurements revealed that the grinding wheel's surface speed, approximately 5,500 feet per minute compared to milling cutter speeds of 100,300 feet per minute, generated forces that were individually tiny but collectively massive. Each abrasive particle removed approximately 1/millionth of an inch of material during its momentary contact with the workpiece. With thousands of particles engaging simultaneously, the grinding process delivered material removal rates that were slow in absolute terms, but remarkably consistent in precision. The thermal concerns that had dominated skeptical analyses proved less significant than traditional theory predicted. Anderson discovered that the high surface speed of grinding wheels actually improved heat dissipation compared to slower milling operations. The grinding zone generated intense temperatures, but the heat concentrated in microscopic regions that each abrasive particle occupied for only millionths of a second. Before thermal expansion could affect dimensional accuracy, the heat dissipated into the surrounding metal and the flood coolant that Norton's machines delivered at carefully controlled temperatures. Most revolutionary was Anderson's analysis of the grinding machine's mechanical design. Unlike milling machines that required massive structures to resist cutting forces measured in hundreds of pounds, grinding machines operated under forces measured in tens of pounds. The reduced structural demands allowed designers to prioritize precision over strength, creating machines with ways ground to millionth-inch straightness and spindles balanced to tolerances that eliminated vibration below levels human hands could detect. The Brown and Sharp machines that Norton had purchased incorporated design features that traditional machinists had dismissed as unnecessary complications. The tableways used hardened and ground steel surfaces that maintained dimensional stability across temperature variations. The spindle bearings utilized precision ball races that eliminated the clearances inherent in the plain bearings common to milling machines. The wheelhead assembly incorporated counterweights that balanced gravitational forces to millionth-inch precision. Anderson's analysis revealed that grinding succeeded not despite its apparent limitations, but because of physical principles that made it fundamentally superior for precision work. By March 1933, James Norton's grinding machines had delivered 12 completed gauge blocks to Pratt & Whitney, each meeting the seemingly impossible 2/millionth-inch flatness specification. The precision instrument manufacturer's inspection reports documented achievements that contradicted established industry wisdom about production machining capabilities. Word spread through American manufacturing networks with the velocity of technological disruption. Engineers who had dismissed grinding as a secondary finishing operation began requesting demonstrations of Norton's capabilities. The components emerging from Brown and Sharp's grinding machines exhibited surface characteristics that seemed to belong in precision laboratories rather than Depression-era production facilities. The visual impact of properly ground surfaces proved as compelling as the dimensional measurements. Traditional milled finishes, even when produced by master machinists using premium cutting tools, showed directional patterns under magnification, the microscopic ridges and valleys that represented individual cutter tooth paths. Ground surfaces displayed no directional characteristics, reflecting light uniformly across their entire area with mirror-like clarity that indicated near-perfect flatness. Norton received a contract in April 1933 that would validate grinding technology beyond theoretical discussions. The Timken Roller Bearing Company needed precision reference plates for their quality control operations, flat surfaces accurate enough to verify the roundness of bearing races manufactured to tolerances measured in millionths of an inch. The specifications demanded flatness within 1/millionth across 12-inch squares, representing precision that exceeded even the Pratt & Whitney gauge blocks. Martin Wheeler, who had spent 4 months working with the grinding machines he once despised, took personal responsibility for the Timken contract. His conversion from skeptic to advocate had occurred through direct experience with grinding's capabilities. The machines that had seemed impossibly slow now appeared elegantly efficient, removing only the minimum material necessary to achieve specified precision rather than wasting metal through the aggressive cutting that milling required. The grinding process Wheeler developed for the Timken plates demonstrated sophisticated understanding of thermal management and material removal strategies. Each plate underwent multiple grinding passes with progressively finer abrasive wheels, allowing thermal equilibrium between operations. The final finishing passes removed less than 1/10,000th of an inch total material, eliminating any possibility of residual stress or thermal distortion affecting dimensional accuracy. The completed reference plates exceeded Timken's specifications by margins that seemed impossible through conventional production methods. Flatness measurements across the 12-inch surfaces showed maximum deviations of 0.6 of a millionth of an inch, precision that approached the limits of available measurement technology. The mirror finishes reflected images with clarity comparable to optical glass, providing visual confirmation of surface perfection that no milled component had ever achieved. Industry publications began documenting grinding's emergence as a primary precision machining method rather than a secondary finishing operation. The Journal of the American Society of Mechanical Engineers, which had published Robert Jamieson's skeptical analysis just 2 years earlier, now featured articles describing grinding's advantages for applications requiring absolute flatness and mirror finishes. The transformation from dismissed technology to revolutionary capability had occurred with remarkable speed, driven by results that couldn't be disputed regardless of theoretical objections. By December 1933, Norton's 3 grinding machines operated continuously across multiple shifts, producing components for customers throughout American manufacturing. The telegram arrived at Brown and Sharp Manufacturing on February 12, 1934, carrying specifications that would either establish grinding as fundamental precision technology or reveal limitations that skeptics had always suspected existed. The Pratt and Whitney Aircraft Division needed turbine blade gauges, measuring instruments that would verify the complex curved surfaces of experimental engine components designed to operate at temperatures and rotational speeds that pushed metallurgical boundaries. The technical requirements transcended anything grinding machines had previously attempted. The gauges demanded not just flat surfaces, but three-dimensional contours accurate to within 0.5 of a millionth of an inch. The curved profiles had to maintain dimensional precision across temperature variations from room temperature to 150 degrees Fahrenheit, the range that inspection operations would experience in production environments. Most challenging of all, the gauge surfaces required mirror finishes on compound curves, eliminating any possibility of using traditional milling methods that struggled to achieve comparable quality on simple flat planes. James Norton assembled his engineering team to assess whether grinding technology could meet specifications that seemed designed to expose its limitations. Thomas Anderson's analysis revealed challenges that made the previous flat gauge work seem straightforward by comparison. Grinding wheels naturally produced flat or cylindrical surfaces depending on their orientation. Creating complex three-dimensional curves would require specialized wheel dressing techniques and sophisticated motion control that Brown and Sharp's existing equipment didn't support. The solution emerged from combining grinding's precision with manual craftsmanship that Norton's team had previously tried to eliminate. Martin Wheeler proposed using the grinding machines for what they did superbly, creating precision flat surfaces and accurate cylindrical forms, then hand-finishing the compound curves using techniques that master toolmakers had developed for one-off prototype work. The grinding operations would establish the fundamental geometry and surface finish quality, while skilled handwork would blend the surfaces into the complex curves that turbine blade inspection demanded. The development work consumed 6 weeks of intensive experimentation. Wheeler and his team discovered that grinding wheels could be dressed to custom profiles that approximated the required curves, reducing hand finishing to final blending operations measured in tenths of thousandths, rather than the conventional removal of hundredths that traditional methods required. The grinding machines established surface finish quality that hand operations merely continued rather than created, maintaining the mirror polish that distinguished properly ground surfaces from traditional machined finishes. The completed turbine blade gauges represented a synthesis of grinding precision and craftsman skill that neither technology alone could have achieved. Dimensional measurements verified accuracy within the specified 0.5 of a millionth tolerance across the complex three-dimensional surfaces. The mirror finishes extended uniformly across flat planes, cylindrical sections, and compound curves, visual proof of precision that seemed to transcend available manufacturing capabilities. Pratt & Whitney's inspection reports documented not just dimensional accuracy but thermal stability that conventional gauge construction had never achieved. The gauges maintained their precision across the specified temperature range with variations measuring less than 0.2 of a millionth, performance that exceeded requirements by comfortable margins. The grinding process had created not just accurate surfaces but dimensionally stable structures that preserved their precision under the thermal cycling that production inspection environments imposed. The success of the turbine blade gauges eliminated remaining doubts about grinding's role in precision manufacturing. By 1936, surface grinding had transformed from controversial technology into the foundation of American precision manufacturing. The machines that James Norton had purchased against unanimous expert advice now appeared in factories throughout industrial regions, producing components that conventional milling operations could never match for dimensional accuracy and surface quality. The 1932 surface grinders had proven that precision manufacturing required not just different tools, but fundamentally different understanding of how metals could be shaped to tolerances approaching atomic dimensions. The revolution extended beyond simple adoption of new equipment. Grinding forced engineers to reconsider assumptions about achievable precision that had constrained design innovation for generations. Components requiring flatness measured in millionths of an inch once considered experimental curiosities, became standard specifications for precision instruments, gauge blocks, and machine toolways. The mirror finishes that grinding delivered enabled optical measurement techniques that relied on light interference patterns to verify dimensional accuracy beyond mechanical measurement capabilities. The economic transformation proved as significant as the technical achievements. Norton's grinding machines, once dismissed as impossibly slow, compared to milling operations, actually reduced total production costs for precision components by eliminating the extensive hand finishing that traditional methods required. A gauge block that demanded 20 hours of skilled hand lapping after milling now emerged from the grinding machine ready for final inspection after 4 hours of automated processing. The precision that grinding delivered eliminated the rejected components that had plagued traditional manufacturing, improving yields that offset the slower material removal rates. The modern manufacturing landscape reveals how completely grinding revolutionized precision work. Computer-controlled grinding machines now achieve tolerances measured in millionths of an inch as routine production capabilities rather than experimental achievements. The mirror finishes that seemed remarkable in 1932 now serve as baseline quality standards for components ranging from semiconductor wafers to precision bearing races. The fundamental principles that Thomas Anderson discovered through careful analysis, averaging effects of multiple abrasive particles, thermal management through high surface speeds, rigid machine structures optimized for precision rather than power, remain central to grinding operations that produce the most precise manufactured objects humanity creates. Yet the deeper legacy involves the validation of revolutionary thinking against entrenched skepticism. James Norton's willingness to bet his company on technology that contradicted expert consensus enabled breakthroughs that conventional wisdom would have delayed for decades. The machinists who initially dismissed grinding as impractical became the craftsmen who developed grinding techniques that established new precision standards. Martin Wheeler's transformation from grinding's most vocal critic to its most effective practitioner demonstrated how direct experience with superior methods could overcome even deeply held professional convictions. The 1932 surface grinders that nobody trusted changed manufacturing permanently, proving that the impossible tolerances of one era become the routine capabilities of the next. The machines that seemed destined to become expensive paperweights instead became the foundation for precision manufacturing that enabled everything from jet engines to space exploration. The mirror finishes they produced didn't just reflect light. They reflected American manufacturing's capacity for revolutionary innovation when conventional wisdom proved inadequate for the precision that progress demanded.